Again, welcome to Biostatistics. This is Unit 16 lectures, which covers our textbook, Chapter 16. Our main topic today is Inference About a Proportion. That's how to analyze categorical data or variables, or how to analyze a nominal variables, which means we have to use the nonparametric test. So mostly we have to test the proportion or the part. So in order to get the proportion, we may have to count or find the percentage of a specific data set. For example, we tested patients and we found out that 30% of the patients tested positive. So in this case, the proportion will be 30% or 0.3. So our main objective is to go through what is a proportions, which again is part of something. We have a population 100% or a sample 100%, and 50% tested positive, 50% tested negative. The proportion of positive and negative are 50% or 0.5. Also, we'll go through the sample distributions of a proportion. We did a sample distribution of a mean, which is using the, when we are using the parametric test, we can test the mean. In non-parametric tests, we are using nominal data. We cannot be able to find the mean. The only thing we can do is either find the mode, counting, or proportion. We should also do hypothesis testing for nominal approximation and also for exact binomial method. Since we are doing hypothesis testing, that will lead us to finding the confidence interval for a population proportion, and also how to find the sample size and power. We know power is the probability of avoiding type 2 error when we are doing hypothesis testing. We have type 1 and type 2 error. Type 1 error means we are rejecting the false HO or null hypothesis. Type 2 error means we are accepting a false HO. Rejecting a true HO and accepting a false HO, both of them are errors. So that's type 1, type 2 error. Now, when we are doing hypothesis testing, sample size is very important. As we said, the lesser the sample, the bad the result will not be good. So our data analysis journey continues with non-parametric tests. So this is our first non-parametric test. Again, in this course, we went through the parametric test. Test user z-score to test the mean, sample mean. We use the t-testing, ANOVA, etc. So, and also we did regression analysis, correlation coefficient. Now, we have two types of testing the correlation or relationship between two variables. If it's a quantitative data, we use the PSC correlation. That's what we already did. That's for parametric tests. We will go through a spearman correlation when we are trying to find a relationship between two variables, but the data type is categorical. So that's a non-parametric test. So in our textbook, we went through Unit 1 to Unit 10, which focus again on stat concept like descriptive statistics and probability. Then from Unit 11 to 19 is our main focus of Biostat 2, which is inferential statistics. So Biostat 1, we did descriptive and probability. So Unit 11 to 15 focus on analysis of quantitative response variable, which is our parametric test. Now from Unit 16, which is our first unit here, 16 to 19 will be focused on analyzing a categorical response variable, which will be non-parametric. In inferential statistics, we have parametric tests, which we have to consider the parameters. For example, is the sample size of population normally distributed, where the mean is, standard deviation, variance. But when we are dealing with non-parametric tests, that's why it's called non-param. We don't consider the parameters. We don't even consider the distribution of the data set, whether it's normal distribution or not. So summarized data, we always have an outcome variable. When we have an outcome variable, we have to check, is the variable quantitative? then we do a parametric test. If it's categorical, we do non-parametric test. So as we said, a non-parametric test, the main response variables we can find is the count or the mode counting. Now, based on counting, we can be able to find proportion. Let's say 10% of the patients tested negative proportion. But with quantitative, we can find the sum, we can find the average, we can find the standard deviation, etc. So those are the two main testing, either parametric testing or non-parametric testing. So we start with the different types of variables, especially in categorical. So mostly in categorical response variables in the medical field, as this course is about statistics, we may have yes or no. For example, here we say classification of a respondent as a current smoker is yes or no. Gender is male or female. So a binary means two. So a binary response variable means the possible solution or answer we can get is only two. Either true, false, male or female, yes or no, positive or negative, classified or non-classified. Cancer can be benign or malignant. That's cancerous or non-cancerous. So whether a patient survive 5 or more years, can be survive or do not survive. Binary response variables, only two outcomes we have. Whether the subject develop a broad crowd, it can be a case or non-case. Only two possible outcomes, so it's a binary response variable. So one outcome is arbitrarily labeled as a success, and the other will be a failure. Except maybe if it's a gender, none of them, either male or female, both are success. But testing a patient for a specific cancer or disease, it can be either you tested positive or negative. Positive means it's a failure, you have the disease. Negative is a success, it doesn't have the disease. So if the process of selection is random, then the number of successes in a sample will follow a binomial distribution with parameters of n and p. That's if the selection process is random. Then the number of success in a sample will follow the binomial distribution with the parameter n and p. Again, we did the binomial distribution somewhere around unit 6. We say a binomial distribution, one of the characteristics is you are doing some try and the possible outcome of the try will be only two, either true or false, success or failure. So we may have the probability of success. If probability of success is 0.7, then probability of failure will be 0.3, which is 1 minus 0.7. So with proportion, using a single simple random sample, the response variable is binary, then the proportion is equal to x by n. Again, x is the number of success and n will be the sample size. So again, to find the proportion, the conditions given is that we have our sample which was collected randomly, simple random sample. The response is only 2. We know binomial, always the outcome of the try is 2. Either true or false, yes or no, success or failure. So in that case, the proportions, which is the number of success in the sample denoted by p hat, is equal to the number of success divided by the sample size. So it's like we're finding the proportion of success. And two of the 10 individuals in a sample have a risk factor for disease X. So this is an example, 2 of 10. So which means the sample size is 2. The number of success or X, the sample size is 10. The number of success as X is 2. Because we say 2 of 10 individuals, 2 of 10 individuals of 10. So that will be the total sample of the population. 2 in the sample have, okay, so the question here is a sample. So 10 is the total sample. 2 out of the 10 have a risk factor for this is X. Therefore, the prevalence of this risk factor in a sample will be 2 divided by 10. Or P hat, which is the probability of success, equal to the number of success divided by the sample size, which will be 2 divided by 10. So our answer will be 0.1 or 10%. So a proportion is an average of zeros and ones. This is our example given here. We have a data set. The observation, or we will say the total sample is 10. How many, let's say 1 means true, 0 means false. So out of the 10 sample, as we saw earlier, 2 were successful. So 2 are 1, 1. The rest again are zeros. So here are the data in tabular form with the variable coded as 1 is risk factor present and 0 is risk factor absent. And the question said again, the 2 of the 10 in the sample have a risk factor of this is X. So risk factor will represent 1, it's only 2. So to find the, note that N is the sample size, the lowercase n is our sample size 10. And the possible X, the sum is only 2. The number of success is 2. So the sample mean will be 2 divided by 10. 2 divided by 10. So we also have the concept of incidence and prevalence. Incidence means the proportion of people or of a sample or population that are at risk with a new case. Incidence will find the proportion of a new case. Prevalence will find the proportion of the total case. So example, let's say we have HIV tested in a population. And we took a sample of 200 and we found out that 50 of them have HIV. We took that sample from the whole population. So if I'm finding the prevalence, I'll just divide 50 by 200. That will give me the prevalence. But if I want to find the incidence, let's say some of these positive HIV patients, they have it 10 years ago, 20 years ago. And we have a regulation that a new case should be less than 1 month. So this means we are not going to use all the 50, because the 50, some of them have the HIV about 10 years ago, 20. So what are the number of HIV positive within a month, the new cases? Let's say we have 5. And then we are not going to use all the population or the sample, but we are going to look at those who are at risk, their behavior is at risk of getting HIV. So instead of 200, maybe we find out that only 100 practice some behavior that put them at risk of having HIV. So in this case, we are going to divide the total number of new cases over total number of people that are at risk of getting the HIV. But when we are looking for prevalence, all the total people who have the case, we don't care it's a new or old case, divided by all the population. So here we say incident proportion, which is average risk, is a proportion that develop a specific condition over a set period of time. So that set period of time will make it a new case. But the prevalence in the proportion with the characteristics at a particular point in time. So again, incidence and prevalence, they are all proportion, percentage of something. But incidence will measure the proportion of new cases based on the behavior, the population that are at risk because of their behavior, at risk of getting the disease. Prevalence will give you at a particular point in time. So all the people who have the HIV positive divided by all the population. So we have an example here which they say we should illustrate, illustrative example, the prevalence of smoking So we have a data set. We collect a simple random sample of 57 adults. And these 57 adults, it revealed that 70 are currently smokers. What is the prevalence of smokers in this sample? You see, here we are looking for the prevalence at a particular point in time. When we take our sample, at that very point in time, 70 are current smokers. So the prevalence will be 17 divided by the whole sample, which is 57. And that gives us 0.2982. We say the calculation should carry at least 4 significant digits. For reporting purposes, the APA Publication Guide 2001 recommend that proportion be converted to percentages and reported with only 1 decimal. So if I'm using APA, I'm going to report instead of 0.2982, I will write to 29.8% prevalence of current smokers. So inference about a proportion, these are some few things we should know. First, how good is sample proportion? P carat at estimating the population proportion. So this means we know when we are collecting sample, we have to make sure that the sample represents the whole population. If there's any bias in the sample, that will affect our decision on the population. Because we know inferential statistics, we collect a sample, we cannot use the whole population because it will consume a lot of time to collect the data from the whole population, and also finance involved. For example, we have 10 million people living in New York City, and we want to do some testing or some research, and we want to test the whole 10 million New York City. It will be a long process. So I'll collect a data of 1,000 people out of there. But the answer I'll get from the 1,000, I'm going to generalize it to the whole population. So here I have to make sure that the sample I collect represent the whole population. So that's the first thing. How good is a sample proportion, P carat, at estimating population proportion P? To answer this question, consider what will happen if we took repeated sample, each of the size n from the population, and also how will sample proportion be distributed? In inferential statistics, we said if we take a repeated sample from a population and we use all the population with that replacement every time we take the sample, the distribution will be normal. And that's the concept here. I took all the sample, size 1, 2, all the sample, and we use all the population. If you find the mean of each sample, it will give a distribution of normal. So sample distribution of a proportion, here we say that in a simple random sample, the random number of success X in such sample would follow binomial distribution with parameters N and P. We discussed this in Unit 6 lectures. Again, this is our Unit 16. Also, the sample proportion, P carat, is a mathematical transformation of the count of success divided by count by the sample size. Proportion will be the number of success divided by the sample size. So when n is moderate to large, the normal approximation to the binomial can be used, which we cover in Unit 8. That's using the normal distribution concept. And this is what we get. If we have a normal distribution, again, the standard deviation will be square root of P standard probability of success multiplied by probability of failure, Q, divided by the sample size. And this will give it the standard deviation. The Q always will be 1 minus P. P always will be given the probability of success. So now let's do hypothesis testing. This is again categorical response data variable. So we are going to test, since it's a categorical data, we cannot test the mean. We are going to test the proportion. So here we say the null hypothesis will be the proportion equal to the population proportion, or the null proportion. So if it's equal, then HA should go against. Either it will be not equal, which is two-way testing, or greater than or less than. So again, PO represents the proportion specified by the null hypothesis, which also sometimes we may say the population proportion. This is what we agree in our previous studies. Let's say the question will be asked that the proportion of people who have a certain disease in 1970 was 0.2. Now I want to do a testing today if it's still 0.2. So yeah, I'll say the P equal to 0.2, and then alternative hypothesis will be P not equal to 0.2, or P is less than 0.2, or P is greater than 0.2. Again, the process of doing hypothesis testing is the same in a categorical data or non-parametric test. Is the same step as the parametric test, like finding the T distribution, etc. So we know first we have to state our HO and HA. The next step, we have to find our test statistics. Again, the formula changes here because here we are mostly dealing with proportions, because we don't have, this is a categorical data. We cannot find the mean, we cannot find the standard deviation. So to do the z-stat, we say it's P caret minus PO. PO again is the proportion for the null hypothesis. That represents the null. Then the P caret over square root of POQ over N. So you can remember PQ square root of P times Q over N is a standard deviation. So that's the same concept. But this is a categorical data. So now when we get the z-stat value, we can go to the table, which is the standard normal table, to find the p-value. Then from there, we can interpret our result. If the p-value is less than the significance level, then we can say that we are going to reject the HO. The p-value is greater than the significant level or equal, we can say that we are going to accept the HO. So the significant level, again, that is optional. So let's see an example here. Here we have a data set and we collected a sample of 57 using the simple random sample method. And we found out that 17 of them were smokers. So we find the p-hat first. So the p-hat will be 17 divided by 57. Now, the national average for smoking prevalence is 0.25. So if the national average for smoking prevalence is 0.25, which means the PO, the question is that, is the proportion the sample significant different than the national average? So our test we want to make is that, is the proportion of the sample today, is it the same as 0.25? So we know HO will be P equal to 0.25, HA will be P not equal to 0.25. So we're doing two-way testing. We already find a P caret, which was 17 divided by 57, the sample size divided by the number of success, or here in this case, those who find the smoke. So when we plug in the values, we get z-stat to be 0.84. Now, I'll go to my table, the standard normal table, to go and look for the value of P. When we do that, we get the value of P to be 0.4010 through the table. Again, this is z-stat, so we use the standard normal table. Now, since it's 0.4, that's almost 40%. And by default, alpha value is always 5%, 0.05, or sometimes we can state it to be 0.10. It can never be more than 0.20. Most of the time, even up to 0.10. But since the P is almost 40% or 0.4, this means the P is greater than the significant level, the alpha. So in this case, we have to accept the HO. There's no any much significant difference than the HO that we have. The HO said the national average is 0.25. The national average for smoking prevalence is 0.25. So that's why here, anytime the P is greater than the alpha, then we have to accept the HO. So here we say the sample proportion is not significantly different than the national average. So when n is small, let's say less than 5 success expected, binomial distribution do not resample the normal distribution. Remember we did this in Unit 8. We can test if NPQ is greater than 5 or equal to 5. If it's greater or equal to 5, then binomial distribution can tend to normal distribution. We also have, if this is not possible, then we have another method called exact binomial procedure. So instead of an exact binomial procedure, such as the Fisher's method, should be used. If this condition is not met, if the sample size is too small, we should use the Fisher's method or exact binomial procedure. So let's go through what is exact binomial method. We use it again for hypothesis testing. So again, we are testing our categorical data. So we're testing the proportion. We say the P equal to PO, which is the claim of the null hypothesis. If that's the case, HA will be either not equal, less, or greater than. Here we say not equal to PO, where PO represents the population under the null hypothesis. So we need a test statistics. But here we are using exact binomial method, so we don't need to find the Z. But test statistics will be observed number of success X. Then we can use the software to calculate the p-value. So the theory of the test, assuming that the X, which is a binomial, you have N, the sample size, and also the PO, the proportion. So for right-sided tests, p-value, the probability to be the variable S should be greater than or equal to X from the exact binomial, again from the binomial distribution. So significant level, so that's an optional. When the value we get is less than the significant level, then we are going to reject HO. If it's greater or equal, then we are going to accept HO. There's not much significance. So let's see this example. We have a T challenge. And here we see an individual correctly identify the order of adding milk to T in 6 of the 8 attempts. Now, can we say that this is better than random guessing? So random guessing means our P will be 0.2 because random guessing equally. So an individual correctly identified the order of adding milk to a T in 6 of the 8 attempts. 6 of the 8 attempts. Can we say that is better than random guessing? Random guessing means everybody have equal chance of getting selected. So we use half 0.5. In statistics, here we are 6 out of 8. So we have 6 out of 8. So the p-value, P will give me 0.145. And in this case, we are using the wind pipe, which is an application. But since the P is more than 10% or even more than 5%, we are going to retain the HO. So here we say there's a weak evidence against HO. It's weak, so we have to accept HO. Significant level we are using here is 0.10, since 0.145. Again, 0.145 is greater than 0.10. We have to again accept the HO. So we use the windpipe application. You can download this again. You can use online, Google, etc. So we can see the exact binomial test. One tail p-value is given to us. So next is how do we find the confidence interval for population proportion? Also, this method is called the +4 method because it will add 4 imaginary points during calculations. It is much more accurate than traditional normal method. So 1 minus alpha 100% confidence interval for P is, remember previously in parametric tests like t-test or z-test, confidence interval, we will say the mean plus or minus the margin of error. Here we are using categorical data. We cannot find the mean. So it will be the proportion plus or minus the margin of error. Margin of error is the same as parameter z, 1 minus alpha over 2 times SE, which is the standard deviation of the sample called the standard error. And here also square root of p caret q caret over n caret. This is also a standard deviation formula. There's a little bit tricky actually, that's why we call it the +4 method. Now to find the S bar, it will be our S, we know S is the number of success, it will be S plus 2. To find the sample bar, to be the sample size plus 4. Then if we know the S bar and N bar, we can find the P bar, which will be S bar over N bar. Then Q bar will be 1 minus P bar, so we can be able to find the standard deviation. So we are going to plug in the Q bar, the P bar over N bar, then Z 1 minus alpha will always be given. If it's 5%, 0.05. If it's 10%, 0.10. Then we can find the P caret, which is normally the S over the N. When we find the P, that is the S caret of, S bar over N bar. So this is example given. We are using the same smoking. A sample of 57, we found out that 17 of them are smokers, so S equal to 17. Now they say we should find a 95% confidence interval for the prevalence of smoking in the population. So I know X, so to find the X bar, it to be S plus 2. And S is 17 plus 2, so 19. I know N, so to find N bar, it will be N plus 4. So N bar, N plus 4, which will give me 61. Okay, so I know N bar and I know S bar, then I can find B bar, which will be, again, X bar over N bar, 19 over 61. That give me 0.3115. Okay, if I know the P bar, I can find the Q bar, which will be 1 minus 0.3115, which will give me 0.6885. So now we have all the values to find the standard error. P bar, Q bar over N bar square root. We plug in the values, we get 0.0593. So now we can go to our plug in the values. But first we can find a Z also. Since it's 95% confidence interval, alpha will be 0.05. So 1 minus 0.05 over 2, the answer you get, you go to the table, we get 1.96. So now we plug in the values. The P was 0.3115 plus or minus Z times standard error P bar will give me 1.162. So it is plus minus 1.1162. And that will be our answer. Remember, the standard error will be the Z1 minus alpha over 2 times the standard deviation, which is square root of P bar Q bar over N bar square root. So we need to find it. That's what we have here, 0.0593. So if you multiply 0.0593 with 1.96, you get 1.1162. Then you add it and subtract from 0.3115. And that will give us the interval. When we subtract, that's the lowest limit. When we add 0.1162 to 0.3115, that will be the upper limit. So we can also use the windpipe to do our calculations here. So here we find the 90% confidence interval, 95 and 99. Next, we go to the sample size and power. Again, anytime we are doing hypothesis testing, sample size is very important. As we said, if the sample size is less, it will affect our result. Our result will not be a good result. Power also makes us to find the probability that we can avoid type 2 error. Type 2 error means accepting a false null hypothesis. So here we have three approaches. N needed to estimate P with margin of error M for confidence interval. And that's what we saw in the previous example. Also, N needed to test HO at a given alpha level and power. And the power of testing HO under the stated condition, we covered it in unit 9.6, 10.3, and 11.7. It has additional background if needed. So this is when we are doing the parametric testing, the Z test, T test, and ANOVA. We always, again, hypothesis testing is good always to find the sample size and also the power of a probability of avoiding type 2 error. Here we have a little bit different formulas from the previous units. To find the N, it will be Z 1 minus alpha over 2 square times P star and Q star divided by M square. M is our margin of error. So here we say the P star represents an educated guess for the population proportion. When no educated guess for P star is available, then we use P star equal to 0.5. Then we run it to the next integers to ensure stated precision. So if P star is 0.5, then Q star also will be 0.5. Now, in N, we need N to achieve M. So suppose our educated guess for the proportion is P star is 0.30. Then for the margin of error of 0.05, we can use 1.9 square, because if alpha Z 1 minus alpha over 2 always will give a 1.9. So Z square means we get 1.9 square times P and Q, P star and Q star. Since we already know the P star, the Q star will be 1 minus P star, so that will be give me 0.7. So we are using the formula here divided by M square. So Z 1 minus alpha over 2 all square, we get the value. If it's 0.05, we get 1.96 all square. P is 0.3, so we get 0.3 times 0.7. Q will be 1 minus P, so 0.7. Divided by the M square, the margin of error. So we get our answer to be 33322.7. And we know that this is a sample size. It cannot be a decimal. It has to be a whole number. So we run it to 323. So the margin of error will be 0.03. So we use 1.96 squared times 0.30 times 0.7 over 0.03. When the margin of error, we see that when it's 0.05, the value is small. When it's 0.0, when it's reducing, then they are demanding more sample size. This tells us that when we have more sample, the error reduces. So N will give us Z 1 minus alpha square root of POQ. Again, POQ is the known P proportion or success, and Q will be 1 minus PO. Plus Z 1 minus beta. So here we find the power. So 1 minus beta Z. Z 1 minus beta is the probability of avoiding type 2 error divided by P1 minus PO. So again, alpha level of the test, 1 minus P is the power of the test, PO proportion that the null hypothesis, P1 proportion that the alternative hypothesis. So the same example we are using, we know the P to be 0.21 for HO, and HA is P is 0.31. Alpha is 0.05, and we have 90% power. And it's two-sided. So we plug in the value, N will give me 1.96. Why 1.96? Because we are using alpha 0.05. So Z1 minus alpha over 2 is 1.96. Square root of PQ, so 0.29, if P is 0.29, Q will be 1 minus point. So if P is 0.21, then Q will be 1 minus 0.21, which is 0.79, plus 1.28, 0.31, then 0.69. Then we have the difference of the PO and P1. Again, this is the formula P1 minus PO. Z, 1 minus beta, and 1 minus alpha over 2. So power, when testing for HO, P equal to PO. So that's the formula 1 minus beta, that is the power probability of avoiding type 2 error, will be the absolute value of difference of P1 and P0, multiplied by square root of the sample size minus Z, 1 minus alpha over 2, square root of PO QO over square root of P1 Q1. Again, P1 is the P1 Q1 is for the alternative hypothesis values, and PO Q is for the null hypothesis values. So we are doing the same example. We have all the value P1 and PO. We have the N, Z, 1 minus alpha over 2, alpha is 0.05, so we get 1.96, PO, QO, 0.21, 0.79, the same thing, 0.31, 0.6, so the sum of 0.31, 0.69 will give me 1, the sum of 0.21, 0.79 also give me 1. So when we do the calculation, we get the theta negative 0.09, we use our table, our answer will be 0.4641, which is, we have 46% chance of avoiding type 2 error. So conditions for inference, first we should consider the sampling independency. Good will be the simple random sample or using the fast meal. Make sure our data or information is valid. Also the +4 confidence interval require at least 10 observations. Then the z-test of HO, which is P equal to PO, require NPOQ to be greater than or equal to 5. This is using the normal approximation. So this will be the conclusion of our, again, Unit 16 lectures, which focus on our first non-parametric testing. Doing hypothesis testing, this time we are using categorical data. So if you are using categorical data or nominal data, the only thing we can do is count it. And when we count, we can find percentage or proportion of something. Example again, we have 300 patients, 75% of them test positive. What is the proportion for the positive test? It will be 75 over 300. What is the proportion for negative test? It will be 300 minus 75 over 300, which is 225 over 300. So 225 tested negative. So again, wish everybody the best. And again, thank you for your time.